In this video, we will introduce our project about life expectancy influential factors. Life expectancy is a significant index reflecting a country's development. A good understanding of the influential factors of life expectancy will assist the public officials in a country to make beneficial policies. Existing studies focus on immunization factors, mortality factors, economic factors, social factors, and other health-related factors. Although there have been a lot of studies undertaken in the past on these three factors, there's currently no study about the number of education years and the gross domestic products per capita. So our general question is, how do the number of years of education and the GDP level would help predict the life expectancy?
The data set we're using is from the Global Health Observatory data repository in Kaggle. It includes many factors from 1649 countries, but in our research, we mainly focused on prediction of life expectancy and have chosen the most relevant factors that might affect life expectancy, including income, GDP, expenditure, population, alcohol, schooling, and status as our explanatory variable, which includes status as a categorical variable, and our independent variable is life expectancy.
Our project consists of two different parts. The first is the model diagnostic and improvements. In this part, we will first check the assumptions, make some remedial procedures, and recheck the assumptions again. On the second part, we will answer three hypothesis questions. We shall start from a very general questions and narrow it down to a very specific questions. They are, do any explanatory variables have significant impact on the life expectancy? The second is, can GDP per capita and the years of education be dropped from the model given all other variables are already in it? The third is, can the interactions between GDP per capita and the years of education be ignored given all other variables are in the model?
For this model, we take life expectancy as the dependent variable y. There are 7 independent variables x. The first one is a categorical variable, country status, including developing and developed 2 levels. Second, schooling. Third, income compensation of resources. Fourth, GDP. Fifth, total expenditure. Sixth, alcohol. Seventh, population of the country. Here is our assumption check for linearity from the plot between the life expectancy and other variables. Except the expectancy is linearly related with the number of education years, other variable didn't show any linear pattern with the life expectancy. The linear relations with other variables need to be improved with a future method. Here is our assumption check for constant variance. From the residual plot, we can see that the constant variance assumption is not significantly violated, but we will try remedying it in the following steps. Here is our normality assumption check. So firstly, we look at the density plot. The density does not follow a bell-shaped curve. Therefore, we speculate our data do not follow the normality assumption and use cuckoo plot to look closer. From the result of the cuckoo plot, there is an obvious deviation from the cuckoo line in the beginning region. Then we use a Shapiro test to see if the model indeed follows the normality assumption. Given the result of Shapiro test is that the Q value is less than 2.2 times 10 to the power minus 16, which means that our data significantly violates the normality assumption.
To identify X-level outliers, we use the head matrix method. The result of it shows that we have about 120 outliers in the X-level. Compared with the dataset, this is a very large number, although not all of them are influential points, which we will discuss in the procedure later on. A remedial procedure to reduce their influence is necessary. Also, to identify Y level, we use the studentized deleted residue. The result of it doesn't show any outliers in the Y level. We use 3 methods to determine any possible influential points. So for DF fits and coexistence methods, we don't find any influential points based on these methods. However, for df-beta's method, we found that all of our data are influential points. So we provide two explanations for this unusual result. The first one, we believe it might because some data indeed are influential. From the QQ normality plot, we notice the starting region of the data significantly deviate from the QQ line. That means some data deviate from the best fit line. And for the second reason, we believe it might because the model includes too many columns. df-betas will report this observation if at least one of these attributes is influential. Since our model contains too many columns, it's hard to find any observation that's not influential in any column. However, we believe two explanations above are not complete. We will apply a remedial procedure to improve the robustness of the model later.
Let's go back to check the linearity. If we will only perform the weighted least square, both the r squared and the r squared adjusted will raise a little bit. If we first perform the box size and then weighted least square, both r squared and the r squared adjectives will reduce from 0.6. If we first perform the weighted least square and then box cox, both r squared and r squared adjusted will raise more than the first model. So we conclude that the third model is the best in the linearity. Let's go back to check the constant variance. As we can see the residual graph and the BF test result, although three improved models still violate the assumptions of the constant variance more significantly, we notice that the p-value of the first model reduces the least, and the third model has the most evenly distributed residuals around the x-axis. So we conclude that the third model is the best in the constant variance. Last, let's go back to check the normality. As you can see the QQ plot there and the Shapiro test result, although three improved models still violate the assumptions of normality significantly, we notice that the p-value of the third model reduces the least, and the third graph has the best fit of the QQ line. So we conclude that the third model is the best in the normality. To reduce the influence of the outliers, we performed robust regression. After the robust regression, standard errors of all parameters have reduced a lot, which means that the estimation precision has improved a lot after robust regression. Although usually the bootstrap method will make the robust regression model have a better constant variance, this output shows that the bootstrap method does not actually improve it. We did some reviews but failed to find any reliable explanations. Therefore, we believe that this is one of our limitations of this project. We failed to provide an explanation for this boot output. So we conclude that our bootstrap method does not improve the model.
In the plot on the left, we notice some collinear patterns. Hence, we performed the VIF test to check on multi-collinearity. Since the value computations are less than 10, we conclude that among all predictor variables, our improved model does not have multi-collinearity issues. None of the variables needs to be dropped. Through a tenfold cross-validation, the root mean square error in the improved model gets significantly large compared with the initial model, since the improved model contains a large lambda value, 3.437. We believe this is elimination for our project because our improved model in fact does not improve the precision in RMSE. We can't claim that the improved model is better compared to the initial model because of the larger RMSE. After all of the preceding diagnostic procedures and model improvement, here is our full model.
So here's our first hypothesis testing result. Our question is about, do any explanatory variables have a significant linear impact on the length of life expectancy? As we can see from the graph, the F statistic is about 386.1, which is greater than the p-value 3.5. Therefore, we reject the null hypothesis and claim that at least one of the predictor variables above has a significant impact on life expectancy.
Here's our hypothesis testing 2, part 1. If GDP per capita and the years of education can be dropped from the model, given all other variables already in it. The non-hypothesis is that beta schooling equals to beta GDP equals to 0, and the alternative hypothesis is that at least one of them, beta schooling and the beta GDP is not 0. The conclusion is there. F statistic is much larger than the critical value. We reject the non-hypothesis. It means although the model includes the variables like family income, population size, alcohol consumption, GDP per capita, and the years of education still help predict the life expectancy. They both have contribution in the model. Part 2. If GDP per capita can be dropped singly from the model, given all other variables, including schooling, are already in it. Our non-hypothesis is beta GDP equals to 0, and the alternative hypothesis is beta GDP is not 0. Our conclusion is that since F statistic is 25, much larger than the critical value 3.84, we reject the non-hypothesis and claim that given all other variables are in the model, GDP cannot drop. It means although the model includes all other variables, including the years of education, GDP per capita still help predict the life expectancy. It has contribution on the model. Part 3. If the number of years of education can be dropped from the model given all other variables are already in it, non-hypothesis, beta schooling equals to 0. Alternative hypothesis, beta schooling is not 0. Since our conclusion is that since F statistic is 252, much larger than the critical value 3.84, we reject the non-hypothesis and claim that given all other variables are in the model, schooling cannot be dropped. It means although the model includes other variables, including GDP per capita, the years of education still helps predict the life expectancy. It has contribution on the model.
Hypothesis testing 3. Do GDP x2 and year of schooling x6 have a significant joint impact on the length of life expectancy? Our null hypothesis is the beta interaction equals to 0, and our alternative hypothesis is the beta is all equal to 0. Since the p-value is smaller than 0.05, we reject the null hypothesis and claim that the GDP and education have a significant joint impact on life expectancy.
Now I will talk about the conclusion for model diagnostic and improvement. Our initial model validates assumptions of normality and constant variance. By exploring and comparing models from different procedures, we found the best procedures are get rid of influential points, use weighted least square to improve the constant variance, apply Box-Cox transformation to improve the normality, and use robust regression and bootstrap method to minimize influences of outliers. And the picture below is our final model. Our 3 hypothesis questions draw the picture from a general level to a specific level. Firstly, at least one of the following variables has impact on the life expectancy: status, schooling, income, GDP, expenditure, population, and alcohol. This conclusion can be explained by our prior knowledge that a country has a higher life expectancy if it commits more budget to the life improvement. Secondly, given our model contains development status, income, expenditure, population, and alcohol consumption, schooling and GDP still help predict life expectancy. Both GDP and schooling have their own contributions in predicting life expectancy. This conclusion implies GDP and education are both significant prediction index reflecting life expectancy of a country. We can hardly drop these 2 predictors. Finally, although both GDP and schooling have their own contributions in predicting life expectancy, their interaction is significant. But even if the interaction somewhat related, they remain to be independent. It's easy to verify this conclusion that a country with higher GDP tends to have a better education system, especially in some developed countries. In the model diagnostic and improvement, we have 2 major issues. Firstly, our bootstrap method for the robust regression failed. We have no idea how to improve and overpass the problem. Secondly, the k-cross validation does not perform well. The RMSE increased by thousands. We claim that the issue was caused by box cost transformation, which lambda is equal to 3.437. Since all the values of life expectancy is at least cubic, the residuals are expected to boost to a very large number. We currently have not learned other methods to resolve this problem. In addition, the three hypothesis question look good. The only limitation for the hypothesis test is that we don't measure if two linear impacts of GDP and the years of education are the same, which means not necessarily equal to 0. This study is probably not feasible because we cannot compare variables with different units. However, our group still holds curiosity to this problem and hope to solve this with future study. Based on the limitation, our group gave 3 suggestions for the future study. First, correct the bootstrap method so that a reverse regression model will be improved. Second, apply more advanced remedial procedures so that the k-cross validation performs better. Finally, answer the feasibility of comparing two linear impacts. If the answer is yes, measure if two linear impacts on the life expectancy are the same or not. A lesson from 3 hypothesis question is that the real statistical world does not consist of true versus false, non-hypothesis versus alternative hypothesis, and reject versus don't reject. Also, different statistical experiments will give different answers. While the statistical p-value equal to 3.427 in -0.05 is indeed small enough to reject the null hypothesis, in the real world it's not always easy to draw a clear limit for two objects. A statistical method or a linear regression is one of useful methods. We shall never be misled and masked by them so that we ignore the ambiguity of the real world. This is a reference for our group project. Thank you for watching this video.